Hi everyone. Today we're going to start talking about chemical reactions. So the things that we're going to cover today are collision theory, energy, and reaction rates. Before we get started, I want to let everybody know that we're going to have a quiz next Wednesday. That's April the 15th. That quiz will cover gas laws that we learned last week, and then collision theory and reaction rates, the things that we're covering over the next couple of days. Like the last covalent bonding review, this one's going to be open note and open book, and it's going to be on campus. Let me know if you have any questions about that upcoming quiz. All right, so what we're going to talk about today is sort of how do chemical reactions occur. So when you mix two things together in a beaker, what's actually happening with the molecules, and how do those molecules come together to form the products that you're trying to make? So the first thing that we're going to talk about is called collision theory. So remember back to kinetic molecular theory, which says that all matter is made up of particles, and those particles are always moving. So we already know, and we've already talked about the fact that if these particles are moving all the time, they're going to collide. And it turns out that those collisions are essential to chemical reactions. All right, so in order for a chemical reaction to happen, molecules must collide. So for any reaction to happen, you have to have molecules actually come into contact with each other. They have to collide. The next thing is they have to collide with enough energy to react. We're going to talk a little bit more about the energy a little bit later, but if they don't hit each other hard enough, nothing will happen. And then the third thing is that molecules must collide with the correct orientation. All right, so if we look here, let's say we've got, this is hydrogen molecules, two hydrogen molecules, and an oxygen molecule, and you can see that they have to collide in order to form water. All right, now, not only do they have to collide with enough energy, but they also have to collide with the correct orientation. So look at how the oxygen and hydrogen molecules come together in this example versus in this ineffective collision. All right, so if the molecules don't hit each other at the right spot, nothing's going to happen, and they're just going to turn back into the reactants here. So they're just going to bounce off of each other, and no product will be made. All right, so whenever we're thinking about chemical reactions, we have to consider collision theory and how and with how much energy molecules are colliding. Next, we're going to talk about the energy of reactions. So chemical reactions can be either endothermic or exothermic in terms of the energy change that occurs during the reaction. So an endothermic reaction is any process that requires or absorbs energy from the surroundings, and that's usually going to be in the form of heat. Right? So if you think of ice melting, in order for that solid ice to turn into liquid ice, that ice has to absorb energy. So that's an endothermic process. Right? Also, if you've ever used a cold pack on an injury or something like that, right? It feels cold to the touch. It's absorbing energy from your skin or from your hand during the process that keeps that cold pack cold. An exothermic reaction, on the other hand, is one that releases energy into the surroundings. And that's usually going to be in the form of heat or light. So if you've ever lit a match, if you've ever lit anything on fire, that process of burning is exothermic. It's releasing heat and light. If you've ever used glow sticks, you crack them and then they start glowing. They're putting off light, right? So any process that releases energy into the surroundings is called exothermic. To determine whether a reaction is endothermic or exothermic, we can look at something called an energy diagram. And an energy diagram is just going to show the energy changes that occur during a chemical reaction. So I've got an example right here. You'll notice on the x-axis, we've got reaction progress, and on the y-axis, we've got potential energy. All right, so if we look from left to right on this green line, we can see that over on the left are the reactants, and over on the right are the products. So that's what I mean by reaction progress, going from reactants to products in your reaction. As far as potential energy, we can think of this as stability. So anything that's up here at the top that's got a lot of energy is going to be very unstable, and anything down here at the bottom is going to be very stable. And so you'll notice a couple of things about this reaction energy diagram. So we can see that we've got a starting point and an ending point, and in between we can see that the line goes way up before it falls again. So this very highest point here tells us how much energy it's going to take for the reaction to occur. So if we look at the energy difference from the reactants to the top of this peak, that's what's called the activation energy. And you have to provide a reaction with at least that much energy in order for anything to happen. Otherwise, the molecules will just bounce off of each other and not turn into products. At the point where we're at the peak of our energy here, the reactants form something called the activated complex. And so it's a really unstable structure that results where bonds are breaking, bonds are forming, and it only lasts for a split second before that activated complex then turns into the products. Endothermic and exothermic reactions are going to have slightly different looking energy diagrams. So first, let's look at an endothermic reaction. So again, in an endothermic reaction, energy is absorbed from the environment. So the reaction is taking in energy from its surroundings. And so what that means is that the products are going to have a higher energy than the reactants because they've absorbed energy from the environment. All right, so if you can see in our energy diagram here, the reactants are way down here. We still have this big peak where we've got our activation energy, but our products end up at a higher energy than our reactants. Right? So energy was absorbed during this process. When you do an endothermic reaction, you're going to recognize it because the reaction container is going to feel cold. Right? So the reaction is absorbing heat from your hands, from the beaker, from the container, and so the reaction container will feel cold because your chemicals, your molecules have absorbed the heat from them. For an exothermic reaction, on the other hand, energy is going to be released into the environment, so from the molecules into the environment. And so when that happens, the products are going to have a lower energy than the reactants. So if we look at our energy diagram here, we can see that reactants are up here around the middle of this potential energy, and the products are way down here. Right? So if the products are lower than the reactants, that means that energy was released in this reaction. If a reaction is exothermic and it's releasing energy into the environment, then the reaction container is going to feel warm. Now let's talk about what happens when you've got a catalyst in your reaction. So a catalyst is a substance that's going to speed up your chemical reaction. It's going to increase the rate, and it's going to do that by lowering the activation energy. So if we take a look at our energy profile over here, our energy diagram, we can see we've still got reactants and products, and without a catalyst, we see that the reaction follows this blue line. So it takes this amount of energy from reactants up to the top of the blue line in order for this reaction to happen normally. When you add a catalyst, what happens is you're reducing the amount of energy that's required to turn the reactants into the products. So you can see that the reaction starts and ends at exactly the same place, but it doesn't need quite as much energy in order for the reaction to occur. So it lowers the activation energy. The important thing about catalysts is that when you put a catalyst into a reaction, it doesn't undergo any permanent change. So the catalyst is the same before and after the reaction. And now you might be familiar with catalysts from biology last year talking about enzymes. So remember, an enzyme is a catalyst that occurs in your body, and what it does is it speeds up all those chemical reactions in your body, turning reactant into products here, but the enzyme itself is unchanged. The last thing that we're going to talk about today is reaction rates. So when I say reaction rate, I just mean how fast or slow is my reaction happening. And to think about what's going to allow a reaction to go faster, we want to think about collision theory. All right, so that first piece of collision theory is that molecules must collide in order to react. So anything that you can do to a reaction to increase the number of collisions is going to increase the rate of reaction, make the reaction happen faster. All right, so some things that we can do in order to increase the number of collisions are think about the surface area of a reactant, particularly when it's a solid. So the greater the surface area, the more collisions are going to happen between the reactants. We can also look at the concentration of the reactants. So the more concentrated, the more molecules there are in the beaker, the more collisions there will be. We can also think about the temperature, right? So remember, increasing the temperature of a reaction will increase the speed of the molecules. So the faster they're going, the more collisions are going to happen. And then lastly, we can do things like agitate the solution, so stir the solution. So if we stir the molecules around, there's a greater likelihood that they're going to come into contact with each other and collide. Right, so we can see here the effect of surface area. So let's say you had a sugar cube and you put it in water. You could have that sugar cube all in one piece, and then the only part that the water could collide with would be the outside here. But if you broke that up and you just put regular sugar into your beaker with water, then you'd have lots of little pieces that the water molecules would collide with, and that would increase the rate of reaction. Here's an example of increasing the concentration. So you can see over here on the left, we don't have very many reactant molecules. If we add more molecules, they're going to hit each other more. It's going to be more crowded. There's going to be more collisions, and that's going to speed up the reaction. Right? And then again, with heat over here, in a cooler environment, the molecules are moving slower, so they're going to collide less often. When we heat it up, they're moving faster. The faster they're moving, the more often they're going to collide. The second piece of collision theory is that molecules must have enough energy to react. So those collisions have to happen with enough energy for the reactants to turn into products. So we can think about some ways to increase the amount of energy or to provide molecules with enough energy to react. So again, temperature is going to help here too. If we heat up our solution, not only will our particles be colliding more often because they're moving faster, they're also going to be hitting harder. So they're going to be hitting with more energy. So heating up a reaction will speed up the rate of reaction. And then again, what we can do is if we agitate a solution, if you stir it, you can provide more energy to the molecules, make them move a little bit faster and collide with a little bit more energy. And then the last thing is the presence of a catalyst can not add energy to the reaction, but it makes it so that the reaction needs less energy in order to react. So it lowers that activation energy and makes it more likely that the particles are going to have enough energy when they do collide. Right, so here I've got a beaker on a hot plate with a little stir, so we can heat up and stir the reaction. And then if we could add a catalyst, that would speed up the reaction even more. Lastly, remember that molecules must collide with the correct orientation in order to react. Right, so they have to hit each other in the right spots for the reactants to turn into products. So sometimes that just depends on the type of molecule. So if there's polarity and there's a slightly positive and negative end, and there's attraction between positive and negative ends of the molecule, that can sometimes help the molecules orient in the correct way. And then again, anytime you're stirring a solution, you're flipping the molecules all in circles, and so it's more likely that they're gonna react in the right orientation and at the right angles. Right? And so you can see here, I've got potassium chloride being dissolved by water, and the polar ends of those water molecules are attracted to the oppositely charged ions, and so that helps them to dissolve more quickly. The last thing that I want you to do today is to complete this simulation. So I've got the notes posted on the Canvas homepage, and you should be able to click here to access the simulation. And what it does is it shows the energy changes that occur when water is used to dissolve 4 different ionic compounds. So what I want you to do is kind of play around with that simulation for each compound and answer the following questions. So what temperature change occurs when the water dissolves the ionic compound? Is energy absorbed from the environment, or is it released into the environment when the water dissolves the compound? And then based on what you answered in questions 1 and 2, I want you to tell me for each one, is the process endothermic or exothermic? And then explain your answer. Tomorrow, you're going to do a lab virtually where you look at some things that you can do to influence the reaction rate of a certain reaction.